Hey, so good morning, everyone. Welcome to CloudCon. I'm looking forward to the program for the rest of the session. It looks pretty interesting. So I'm Richard McDougall, and I'm in the office of the CTO at VMware. And what I want to do today is talk a little bit about some of the experiences we've been having working with our customers on big data solutions and some of the implications that has on the applications you build and the infrastructure approach to building out the clouds that would support these. So we think about big data. What is it? Historically, it's been about things like business intelligence and bringing a lot of data and doing retroactive mining on the data. But really, it was a turning point when some of the big web giants like Google, Facebook, Twitter came in and really sort of changed the way that they were doing analytics. If you look at what Google did very early in, they had to solve a big data problem. They had to create the web index for the world. So what did they do? Instead of using big vertical machines, they took a big data approach, and they built a software layer that could store all that data economically on cheap machines, and they could do analytics on top of it to do things like compute the page ranks. So when you searched, you actually got the item you're looking for. And so they did this by creating the MapReduce algorithms and the Google file system underneath, and then parallelized that so it could run on thousands of machines. So the big data terms really sort of grew up in these web giants, and that's something we became familiar with in those types of companies. But what's really happening now is that it's not just for the web giants. We're seeing it move into practically every enterprise we talk to. This is a fundamental transition that is occurring right now. So pretty much every market segment we look at, be it healthcare, retail, they're doing some sort of fundamental transition to their business through a big data platform. And it's not something that's just plugged in the side of the business. It's actually becoming the forefront of the business. Like, this is how we strategically differentiate from our competitors, by being smarter about the way we run our company, being smarter about the way we know our customers, being very clever about algorithms that can differentiate themselves. So this is the transition that's occurring, and I think this is actually pretty fundamental to cloud and cloud applications. We used to think about cloud being for like our web apps and all the other pieces, and big data being something on the side. We're now seeing a collision of the two of them, where the applications that the enterprises are building have some or many aspects of big data right inside of them. And so the real-time applications that you're going to when you go onto a website are fundamentally some architecture component of big data there as well. So what I want to do is just walk through a couple of the examples of things that we've been working on with our customers, and then look at the implications of those to see how that affects what we need to do about how do we build applications, what are the major components, are there any patterns? And then we'll look at the infrastructure implications of those as it comes to cloud out of that as well. So in this first example, if you look at the retail category, retail is sort of going through a fundamental change. Retail used to be about selling to customers, and you would retroactively find out, like, how did your product do? You would do analytics on it afterwards. At the end of the month, you could do some reports, or you could get some sort of customer feedback. Now it's all about being very connected with the individual customers. So one of the examples here, eBay, they've gone through a big transition about how to understand every single one of their users on the system. I think they used to use big data historically just for things like fraud detection after the fact, market segment analysis, sort of looking backwards. Now what they've done is they've calculated that if they can understand everything about every individual, they can target those individuals differently. So when you go to search on an auction site and look, like you do a search, it's going to throw things back at you which are very context specific to you. And it's going to be based on something you're doing immediately, and it's going to be based on something that they know about you over the past several months. And so one of the things that's interesting is if you think about the data side of that and how much data they need to collect that, they set out to collect every single key click, mouse hover, everything about every individual for 2 years. And that means that they calculated that would be approximately 200 petabytes of data that they need to store to get all that information. And then they can do analytics on top of that. So how did they get to that point? Because that's a phenomenally huge system. Well, what they did was they went and brought some data scientists in. It's a new term that's being used for people that really specialize in this type of analytics, that really understand the data. And they came up with a set of hypotheses, and they said, well, if we collect this type of data, then we think that we can actually increment the revenue on sales by X%. So they came up with this hypothesis, went to the board of directors and said, look, this is going to be a big investment, but we can prove it to you. So why don't we do a small trial? We'll start off with a small number of machines, and to order a scale of like maybe 500. That's a fairly small big data cluster in some senses. And let's see if we can actually show and demonstrate the difference in the attach rate of the customers. Like, how many customers can we actually get to buy more stuff because of that? They went off and did this pilot, and they were able to prove within 6 months that they were able to increase the revenue of the company just through personal targeted marketing. And so that immediately led to the subsequent investments. And so they got approval to grow this cluster out. And so the numbers that have been thrown out there are quite phenomenal, but they're heading towards this state where they can collect that 24 months of click and mouse click analysis for 2 years, and building out that cluster sort of to 200 odd petabytes in size. So there's a couple of things that come out of this. First is an enormous amount of data that needs to be collected and processed. The other is sort of the pattern about how this emerges. We see this all the time inside our customers, which is we have a hypothesis, let's do a big data installation and prove it, and let the data scientists sort of experiment with that for a while, put it in production, and from there it just grows like crazy. And so it's typically growing at a rate of like 50, 60% per year and from that point forward. So the patterns we're seeing are, let's start with like small clusters, 5, 50 machines, and then Hadoop tends to grow upwards from there at a very rapid rate once it's been accepted, for example, as one of the technologies that fits in this space. So that's getting to know the customers through clickstream analysis to the extreme, and I think this will become a very standard procedure going forward. The other that's affecting retail is, there are many others, but sentiment analysis is another one. And so sentiment analysis basically means that we can listen to what the public are saying immediately through some of the things like Twitter. So we can take the social network, the fire hose from Twitter, and then we can analyze that, and we can listen to the tone of what people are saying. So if we can analyze the words and translate that into a score, then we can really know immediately how some of our products are doing. So retailers all of a sudden, instead of having to wait for market reports to come back, can know literally the same second when they release a product, how that's being perceived in the industry. There's actually a couple of examples out there where it's actually gone a little bit further than that. So some people have built prediction technology which can actually predict how a product will come out before it's released. And so what they're doing there is that if it's a well-known product, I've seen this done with movies, I've seen this done with regular product, then you can actually sort of listen to what people are saying and get a tone back of people saying positive things about this or negative things in anticipation of its release. So being able to find out ahead of the curve is actually phenomenally interesting information. So retail is really moving into this predictive analysis and being very connected with a customer, and it's changing the way that retail works completely. So let's have a look at that. So what are the implications of actually building a system like this at that scale? Not everyone's going to be at the scale of someone like an eBay, but most retailers are facing millions of customers. So the systems that people are building in place are actually quite large, and eventually we'll get to this type of scale. So what we've got basically is information coming in. And so we've got information coming in that needs to be stored and processed. And we talked about two different examples here. One is from the social networks. And so we've got social networks feeding information about people commenting on Twitter and Facebook comments and so forth about products. And then we've got real-time streams coming in from the actual use of the storefront. So if you're on Amazon or on eBay and you're clicking on that page, then all of those clicks are coming into the system as well. So vast amount of data, millions of items per minute coming into the system. And the first thing we need to do is process and store that information. So what I'm going to do is just unfold a little bit of a pattern here that we saw. The way we got to this is we went out, talked to a bunch of customers that said, what are you building and what are these systems doing? And we found there was actually a very common pattern behind the system. The way the components are put in place and the flows between them are quite similar. A lot of the technologies vary at this point in time. There are a couple of pieces like Hadoop that are fairly central to this. So this system is pulling all this data in, we're processing it, and we're doing two things. We're processing it because we might need to react in real time. So if you're on Amazon and they want to make a recommendation about you should look at something else, you've got 500 milliseconds to offer someone something in that time it takes to render the screen. So we really want to be able to turn that around very quickly. Now, we don't necessarily want to do that immediately without any context of that user. So if I'm on Amazon and I want to be able to look at an item and it wants to tell me about something I'm interested in, it's not just going to look at what I clicked in the last 5 minutes, it's probably going to look at what did I buy in the last 6 months. So where does that come from? So now we've got some real-time and we've got some historical data coming together. So basically what's going on is people are reacting in real time and we're storing all that information in some sort of platform. And in this other eBay case we talked about, 200 petabytes for that storage platform. It's a scale that's beyond anything that we would normally plan for in a web app. So then what we're doing is we're figuring out how to process all that information. So something that might not be instant, something that might take minutes or maybe even a couple of hours to process, but now I can go back and look through the last 6 months of buying patterns and build up an individualized graph of us as a person and figure out what other things we looked at, what our interests are, and so forth. This is where Hadoop comes in. And most commonly, Hadoop is used for a variety of different things, but Hadoop is particularly interesting because it's a data parallel system. So I can take one of those queries and I can launch it across thousands of machines in the cluster. And so it's a very unique environment in that I can quickly harness a very large cluster of machines to process that quantity of data. So if I've collected that 200 petabytes of data and I want to run queries across it, it likely is going to take hundreds or thousands of machines in parallel to be able to process it in a reasonable time. So we'll talk a little bit more about Hadoop, but Hadoop is having some great success in this part of the market where we want data parallel processing against lots of data. The data science comment here on this part is, so now I've got all this data stored, I'd really like to be able to feed that real-time system that's triggering on the user's activity on the website. And so what I need to do is somehow take that historical data and put that back into the real-time system as a set of rules. So little algorithms that might say, these are the few things that that person's interested in, a very small amount of data at that point in time, or maybe just a simple rule. So the data science part of it is we've typically got a group of people who specialize in understanding that part of the data and then wiring the output of those longer executions back into the real-time system for the web page rendering. So data science is working here. Now the bit in between, what I just described then is a little bit manual. We've got people that are manually looking at the algorithms and the data and then pushing that back to the production system. What's emerging here is a new set of technologies around machine learning. This is not a new mathematical area, but is a relatively new processing platform for applications. So if we can automate that process of understanding that masses of data and figure out the trends and the correlations and push that back into the systems, then we can close this loop a lot quicker. And so there's an enormous amount of activity in commercial companies and startups about automating those algorithms on the data through machine learning. So if you look around at some of the most interesting companies that are providing big data, like half of them are sort of machine learning platforms that are able to automate this process of learning about the data and then automatically reacting to it. So then we have basically some building blocks, which are pretty fundamental, and you'll see these appear in some other examples there. So we've got the data coming in, we're reacting in real time. That real-time reaction is typically an in-memory system. It's a grid of in-memory systems, very low latency. Things like Gemfire, UC Berkeley Spark. There's a set of technologies there that are very good at in-memory reaction. We've got a place to store all this data, and this could be Hadoop, or there's some other technologies that fit in that space as well. We've got our parallel processing, and then we've got our machine learning. There's obviously many other pieces that fit on top of that, but this is the core components. And I think the key thing on this pattern is that cycle getting closed by learning over historical data and then using that to program something that can react in real time. And this is a very common pattern. So let's think about sort of the implications of something like this. On that eBay example, I'm storing every single key click and mouse hover for 2 years. About 200 petabytes of raw storage to do that for 2 years for that user base. So if you look over time and say, okay, what's the implication on systems? Well, I've got to have a lot of processing, but there's a big implication on storage. And so here is just a quick comparison of the traditional data that a company would store in their traditional systems, like their transaction systems or the databases that host the web apps and so forth. It grows, and it grows at a reasonable rate every year. But you're not ingesting a huge amount of new data into those types of systems. But when you start doing something like collecting every single key click and log analysis for log analysis later, the amount of data collecting is just on a completely different trajectory. So you can see here, there was a transition in this customer where it went from the big data side of it being a smaller part to completely eclipsing the amount of data in the rest of the enterprise. And that was the big moment that caught a lot of people's attention, is like the big data systems can actually end up bigger from a compute and storage perspective than the traditional processing systems that you have for these web apps. And this can happen pretty quickly. So the implication of this is that we need to think carefully about the scale and economics around this. So storage-wise, we're collecting so much data now because of these systems. That was just one example. We'll look at a couple of others. And it's predicted that, well, it's actually a fact that we've now surpassed the point where machines, like this clickstream analysis and other log data, are generating more data in the world than people are. And so we're now entering a new generation where machine-generated data is just accelerating the amount of data that we're storing. The stats are we're collecting an exabyte of data every minute now. And so we think about that, that's like 20 times the size of the Library of Congress every minute that's being stored. I think it took something like up until 2003 to get to the first exabyte. And now we're doing this every minute. So the rate of this is just growing 50% year over year, and just will continue to grow from more and more of these sensors and different ways of getting data on the system. So we fundamentally have to change the way we think about storing the data and processing the data, and it will become relevant to all of our core applications as we continue on. So this is another example. This is one that I really like because the amount of data that they get out of the system is phenomenal. Like, there used to be a canonical example a while ago that CERN would generate a petabyte of information when they smashed the atoms together at that point, and they could never collect that much, but they could collect as much as possible. And that was a typical high-performance computing app. Well, so jet engines are now being instrumented and actually becoming a source for big data. And so there's a lot of activity in this space for monitoring and tracking equipment and plant, and the amount of data that comes out of these things is quite phenomenal. So a single jet engine produces about 10 terabytes of data every hour. And so huge amount of information coming out of this. If you collected it all, it would be 90 petabytes just for one engine in 1 year. So do the math on that. We're obviously never going to store, in theory, that much information. But if you can learn from that information, you can do a lot. So historically, what people have done with jet engines and other machinery equipment is they'll do things like monitor vibrations from a sensor. And they'll figure out, well, that vibration means that it's increasing and it's at a different frequency. There's likely to be some sort of material malfunction inside that mechanical equipment, and it's going to break sometime in the future. So well before, hopefully, anything goes wrong, you know that there's sort of leading indicator of something going wrong. So that's historically, that's the type of information you would collect, and there will be a very simple set of rules to take that 10 terabytes of raw information and probably just sift out the couple of little bits of information that are meaningful and then use that to trigger an alarm. That was the old way of doing it. That's probably the existing way of doing a lot of this stuff. With analytics on a system like this, you can really start to figure out the historical trends. So if you can apply some of the same techniques, you can say not only has this vibration reached a threshold, but over the last 6 months it's increased. And I know I can forward predict that there's actually going to be something going wrong because of the history that I can keep on this. But you can go a lot further than that. So now you can actually start to bring that information back. And if you can bring it back to a central place, you can now start to say, well, what are the vibration patterns I'm seeing across all the jet engines in the fleet? Am I seeing a common trend here? Is there something that's actually going wrong in manufacturing across that entire product line? So now I can start to get really intimate product feedback from those devices that I'm making at a scale that we've never been able to do before. So we're really able to do early detection of faults, but we're really able to understand exactly how that product's doing in the field and in mass against all the other environments that it's going through. So that's a pattern that we see happening across the industry as well. In product engineering, it's a sort of very interesting area. So cars, for example, the new Teslas that we're seeing driving around, they're all connected. They're all collecting an enormous amount of data. They're storing it in the car. They're sending it back to the factory as well. And so what they're able to do with that, for example, is look at things like how does the battery pack do? How does the one of 6,000 cells do in these conditions and those conditions in New York, in the ice, in the rain, all these different areas, and bring that back and turn the product engineering around very quickly so they can see exactly how things are doing. It's like you've got a giant test fleet out there, but it's actually your production product, and it's constantly giving you feedback. So that's a really important transition in the product engineering. If you can do that and you can have all your products connected, then you can see a lot that you couldn't see before. And again, a lot of data now. So we're not just talking about every jet engine, we're talking about every car. And it won't be very long, well, it literally will be every car is doing this, and all the manufacturers are trying to store this amount of data. You'll see this in a bunch of other areas as well. So really, this transition, proactively maintained product is occurring very rapidly. This particular engine is from General Electric, and so GE have been quite vocal about this being a huge transition for them and big opportunity. They're doing this with jet engines. Their mission is to do this with all the products they sell, including all the way down to like refrigerators in your home. And so they want to know, for example, is the compressor in your refrigerator cycling too often, and that's a leading indicator that it might fail, and they're going to send someone out to fix it before it fails. And so they want to do this across the entire product suite, and that's going to revolutionize the way that they deliver service, and it's going to give you a much tighter integration with products so they can build better products going forward. Really big change. So you'll probably have seen that GE and Pivotal, which is a group that's owned by EMC, focused on big data with VMware and EMC. There's been an investment from GE specifically in this area to develop the platforms to run the big data systems on top of this going forward. So they've got a big investment in the big data lab and applications that they're building out to make it a common platform that the entire company can use going forward. So let's look at the pattern here. It's similar. It's not exactly the same. I think the difference here that is first notice, you're going to need to do some analytics out on the site, wherever these devices are. So now we're actually talking about deploying applications that not only will land, say, in a data center or in a cloud, but the applications actually need to run where the device is. So in the GE case, they want to run an analytics application on the plane. And they want that analytics application to be able to filter down the data, keep the history, and figure out what's important, communicate that back, give some sort of summarized statistics back that they can analyze across the fleet. And then if they need to, they can reach in and pull more data out. So you've actually got this disconnected analytics going on in the system as well. So it's very similar approaches, but the machine learning and the analytics platforms need to compress down and be able to run in this distributed form as well. So lots of interesting technologies there. They're looking at using the Gemfire platform, for example, as a real-time engine to run analytics out in the site and then have that communicated back in disconnected mode to the central site. You still want the central site because that's where we're going to pull all the information together and do the cross-fleet analysis on the system as well. So the platform looks reasonably similar. Here we've got Hadoop being used in this case for parallel processing on doing the data science analysis. So when I want to analyze all my engines in the fleet, I want to figure out how they're doing and I'll look at the common patterns. Then you've got a team that's actually looking at all that data they've collected at scale inside the infrastructure as well. So, and again, machine learning is being used for this. So similar set of components used for this application. The disconnected mode is different. And I think this reinforces the rate of data that we're collecting as well, that 10 terabytes per engine. Somehow we've got to get a lot of that data back to the mothership, and there's an enormous amount of data that's being collected over time. So I predict that they will have, in this GE case, an enormous farm, much bigger than the eBay example we worked through, that stores all this information about product in the field. So those are a couple of examples of how things are changing. The effects of social networks, geolocation, sensors from different devices are all feeding all this enormous amount of information in, not just for post-analytics, but we need to act in real time on these and fuse them with the online applications we're building. So we're building our cloud apps that might be HTML rendered, interfacing directly with users, but we need to think about like where's the big data component of that? Where's the real-time engine that's actually reacting in real time and fusing that with the historical data? So our applications now have to have this critical component of big data in them. And this is sort of interesting. So what we've seen historically is as the big data environment grew up, it became this orphan on the side initially as an experiment, and it sort of grew up from there. And then we suddenly realized, well, we need some machine learning. So here's another little cluster over here for machine learning. Here is some real-time analytics. So that's my in-memory grid that I'm building. And these things tend to be quite separate. And so very quickly, you have all these different environments growing up. And so what we've been looking at is, with our customers, is how to apply cloud technologies and build a common infrastructure underneath all these applications. And I think it's a really critical point because what our customers have been telling us and what we've been doing in practice is finding that you don't want to quickly set up this separate environment that doesn't have any cloud technologies. Like go back to the physical world and have the application developers know about physical machines and have to wait 3 months to get the machines installed. What they'd rather have is a platform which they can just add whatever components they need rapidly, programmatically and then get on with building the application they care about. And so with things like Hadoop, Hadoop's sort of a blend between a physical environment, a physical infrastructure management platform and an application platform. Yet it works really well to break those into two layers. So Hadoop, for example, becomes an application platform, and you can use cloud infrastructure to be the infrastructure management platform. And then you can put alongside of your Hadoop your machine learning and your big SQL and your in-memory databases and all the other components that would run alongside of that as well. And you can deploy them more quickly and not have to wait for those things to be deployed. So what we look at here is a transition from a set of silos into a software-defined cloud infrastructure. And by software-defined, the premise is that everything in your cloud should be completely API programmable. And so not just the compute and memory, which is typically when we think of virtual machines and spinning things up in the cloud, we're spinning up 3 or 4 virtual machines here or there. But all of the network, and in these cases that we've just reinforced, all the storage part of it has to be completely programmable. So if I need to have like 100 terabytes of storage over here for this application, I need to be able to do that programmatically without having to go and wheel in some big expensive machine that's for storing that data. So I really want to be able to have a completely software programmable environment and get all the storage, networking, compute that I can get at this point for those applications. So the software-defined data center is really fundamental to enabling the agility of these applications. So I can deploy quickly. I can deploy applications on demand. I can use the same techniques, in theory, that I've been using for my cloud applications and our other VMs to be able to deploy those in the infrastructure. I can also leverage other capabilities of a good cloud infrastructure platform. So I can consolidate workloads. We hear that some of the big data clusters, even some of the bigger ones, have like 10 to 20% utilization. So why not use those other resources for other parts of the system? And so I can increase utilization, lower the CapEx cost. And by doing that, I want to be really sure that I'm not putting anything in danger. So if I'm running this enormous analytics application alongside of my important web application, I don't want to have one crunch the other. So what you really want there is some sort of isolation around them as well. So these rules that we've applied to deploying in the cloud also apply for big data. Now, the 3 fundamentals of mixing workloads on any system have been these 3 for quite a while, which is I really want to be able to focus on making sure that resources are separated. And so from a resource application, I don't want the greedy application to take all the resources. I want to make sure that the faults are isolated as well. So if I've got an application which is badly written, I don't want it to take down other parts of the system. We had a good example in one of our big customers where they literally did have a Hadoop newbie come in and write one application that took down 1,000 nodes. So you really want to be able to isolate that from happening. And from a privacy perspective, you want to be able to isolate off the critical pieces that are private from other parts. So from a data privacy perspective, there are all sorts of implications here. One example is that at one of the big web search companies, someone figured out that all the data in the Hadoop system actually is all key-clicking or page impressions, and that Hadoop administrator, if they ran the right query, could figure out what the past page impressions were and what next month's were, and that directly related to the financial results of the company. So immediately, the Hadoop administrator became an insider. So you don't want that to happen. You want to be able to say, no, that piece of data is private, and only these people can see it, and other parts of the data are more public, and so anyone can see that data. So we really want to be able to separate off the security part of it as well. So these are 3 things that we need, and we've found that the software-defined data center and virtualization techniques are really good at putting these boundaries around applications. And so we can deploy a Hadoop workload in an environment and give it a specific set of resources. We might be able to let it grow and shrink. In fact, that's actually one of the key things that we've been doing with Hadoop on virtualization, is allowing it to grow dynamically based on the immediate resource. But we can put bounds around it. So yes, you can grow, but you can't use more than this amount of resource. We can also give every environment, or whichever environment we want, its own software environment. So this Hadoop environment, for example, can have this version of Linux and this version of Hadoop, whereas this machine learning over here can have a different environment, and the 2 can't see each other, and the configurations are completely separate. And then from the privacy perspective, I can isolate off the ability so that you can give root access to different virtual machines, and those users can't see the other parts of the system as well. So the strong isolation is really critical as we mix these workloads, and it's particularly important when you've got that much sensitive data in the system. And this is all possible in a virtualized cloud infrastructure. So a couple of the points just on different parts of the system. So the storage area, I think we saw some of the volumes of data that we're collecting, phenomenal amounts of information. So what do we need out of a storage system? I think our experience in the past has been a lot of the storage, that other line we saw down the bottom that wasn't growing very fast, has been serviced by traditional storage like SAN and NAS vertical systems where a lot of the functionality was in data functionality, but it was a lot more expensive. And so if you're going to store a petabyte of data, in fact, from those graphs, those customers are already thinking about storing tens of petabytes of data. And I was working with a customer this week that is evaluating a storage system, and they had a couple of vendors in that said, yeah, we can grow up to 20 petabytes. And they actually crossed them off the list, and they said, that's not enough. Like, you need to show me how you can store 100 petabytes of data, because that's the trajectory I'm on to grow. And so some of these bigger data systems are thinking already at the scale of 100 petabytes or more is the design criteria for my storage system so that I can bring all this data into the system. So we've got to go and think about how do we build that? What are the systems that we need to be able to store that much data? At the same time, from all those examples we saw, we need to be able to have a system that can store data not just for Hadoop, for example, or not for just a single purpose. So we want to be able to have a storage system that can deal with the machine learning aspect. Maybe you want to run SAS and do some numerical analysis, so we've got to store that data as well. We want to have Hadoop. So we need a storage system that's capable of supporting mixed workloads. And if we get to that point, now we can have a common infrastructure. We've got our compute and memory. Now we've got a storage that can actually speak the protocols, NFS or files or Hadoop. And if we can get to that point, now we have the ability to have a common platform underneath with the economics. And lastly, it really needs to be able to solve the privacy issues that we were talking about. So if you're going to have all the data in place, then look for the attributes on that storage system that has really good encryption, access control, authorization controls that are fine granularity so that you can partition off which parts of the data can be seen by different organizations or individuals. So if we look at what's going on in the industry around storage systems, this is the next big change that's coming, is a move towards pure software-defined storage that gives you a tremendous difference in cost economics. And so if we look at where traditional SAN and NAS is, it's typically where that orange bar, it's sort of $1 to $5 per gigabyte. And so here, we've got a lot of value. Like, these storage systems have been around for a while. They're very high IOPS, and they've got a lot of storage management capabilities in them. And so those, for their purpose, are actually extremely valuable. I can do replication and all the other things that go with the data sets. But if you look at some of the scale-out solutions, NetApp and Isilon have a few of these, then the price points are different. They're not priced per IOPS, they're priced per gigabyte of storage. And so they're priced assuming that you're going to buy a few petabytes of storage. And so the price points are down around the 50 cent per gigabyte range. So it's almost 10 times lower if you look at it from that perspective, somewhere between 2 and 10 times lower. And those solutions typically apply sort of you can stretch this a little bit, somewhere if you're buying half a petabyte to sort of 5 petabytes, 10 petabytes. Those solutions are actually growing like crazy in that space right now. Those are still hardware solutions, but they're horizontally scaled. And the horizontal scale gives you better price performance. The other thing that we need for big data is lots of parallel bandwidth. And those scale-out systems are actually really good at doing that. Instead of having one machine, one storage server that can pump out a gigabyte per second, you've got hundreds of nodes ganged together that give you hundreds of gigabytes per second. So the cost and the bandwidth is there. The next transition that's occurring above that is that the distributed object systems are allowing you to use pure software and scale out on a large number of commodity nodes. And so this is emerging now, and we're enabling this through the cloud platform as well. And the technologies are software technologies that make reliable storage out of commodity hardware. And so this is where Hadoop's HDFS component is pretty famous in this space. It can take the machines and their local disks, replicate across them, and you can store a lot of data. HDFS doesn't necessarily have all the protocols to speak to the different applications, so it's not POSIX compliant and so forth, but it does suit the need of Hadoop quite well. There are other solutions out there. MapR is another one. It's a file system that can be used for Hadoop, but it also has a POSIX and NFS access. So now I can run all sorts of other stuff on that storage system that are not just the Hadoop protocol. And so now mixed workloads comes in, which was one of the key things that we wanted. And there are a bunch of other open source projects too. Startup/open source projects, Ceph, there are a bunch of others out there that are quite relevant. And so these storage systems can run in the cloud environment. You can deploy them on top of machines with local disks using virtualization today. And then that gives you the storage layer that sits on top of the local disks that gets you petabyte scale storage that then can let you run all of your applications on top of it. So lastly, on the networking side, are there any big things that we need to know about networking? Like what's just around the corner there? And I think that the high-level thing about networking is we want to make sure that from a privacy perspective, we can provision virtual network LANs for these clusters as well. So if I've got a private big data environment that I don't want everyone to see, I may actually put that in its own virtual LAN. And so some of the software-defined networking concepts that are now in the products that are shipping are very powerful there because you can put these in their own virtual network. But beyond that, there's a big change that needs to happen on the infrastructure side. This won't happen overnight. You're not going to be able to take this away and say, like, go change my network tomorrow. But this transition is occurring, which is that the types of networks that we build need to be able to deal with the extreme bandwidth you have on these types of systems. So if you're processing Hadoop on 1,000 nodes, you're generating like many terabits of data, like transferring between the machines. The current networks we have in place are not set up to do that. So the current model of putting aggregation switches above the racks, for example, you get a lot of bandwidth inside the rack if you've got a nice terabit, a nice 10 gigabit network inside the rack. But as soon as you try and go between the racks, there's not much bandwidth. Whereas some of the new designs and products that are enabled to allow you to get a full cross-sectional bandwidth across the entire data center. So we're seeing this transition actually occurring. Big data is seeing this, and actually the software-defined networking components that build virtual networks across multiple parts of the data center also want this. And this is an example of a different network design called a CLOS network. It's taken from the telephone industry from the 1950s, but people are using it now as a way of interconnecting all the switches, top-of-rack switches. And the net result is you get full bandwidth between any point to point in the network. So full cross-sectional bandwidth, and you get flat latency depending on where you are in the network as well. And so these are becoming more standard patterns, and some of the switch vendors, like Arista, have enough ports on the switches to be able to do the cross-connects required to build these CLOS networks. So CLOS, Factory, Leaf and Spine, there's a bunch of technologies that are being used to achieve this type of networking. So you will have to build a network that supports these types of bandwidths for these big systems as well. So what we end up with out of that is a infrastructure which can be fully virtualized and fully cloud. It will be different to what you put typical cloud applications in it. It'll have different storage, have different networks, for example, but you definitely can get to a consolidated storage platform. So just in closing here, we have a couple of examples of customers. I'll just go through one. This is a customer that we've been working with, and they've completely moved all of their analytics and big data onto virtual. They've just a couple of interesting quotes here. They just won't do it on physical anymore. They will only do this on a cloud platform, and that lets them get the environments very rapidly, and they can spin up different types of workloads. You can see the mixed workloads here, Hadoop and database, so forth, all on the same platform. So this has worked out really well for them. So just in closing, we really are seeing a transition. The types of applications that people are building are moving from back office analytics to real time. And this collision that we're seeing between the web apps that we're building and the big data apps is here now. And so those are the types of apps we need to build. And we really want to be able to look to the infrastructure and build and design a common infrastructure. And it is possible to build a cloud infrastructure that can cater for these both types of applications on the same platform. So in closing, thank you very much. It's So I think we've got a little bit of time for questions and answers if we
that was terrific. Questions from the audience? So there are mics, there's a mic right there, so if you have any questions, please do walk up. And while you're discussing that, you mentioned Hadoop quite often, and in fact there's an entire full Hadoop class going on today.
Oh, good.
Can we assume that the idea of big data and Hadoop being tied is now settled, or are there still many other options available? Hadoop seems to be a popular one today, but there are others that people should be looking at as well.
Yeah, I think that there's definitely a change over the last couple of years where there's a lot of new parts of the platform coming in that are different parts of the ecosystem. And so we see the Hadoop, the core of Hadoop becoming an application platform. And so MapReduce and the ancillary components that sit on top of Hadoop are here to stay, and the open source community is rich and is thriving. At the same time, there are other big data. There are some big SQL databases, the in-memory grids, and those tend to not use MapReduce. Those tend to use storage and commodity clusters. And so the community around big data has definitely been supplemented by a bunch of things that are other than MapReduce. And MapReduce will be here forever, but we'll see other technologies like the big SQLs and the in-memory grids and everything all fitting on the platform at the same time.
Okay, great. Question?
In an early slide, you showed real-time feed into the big data analysis, and maybe that's from a collection standpoint, because it seems that it breaks down, I think, in terms of MapReduce is inherently batch, and so if you have real-time data that you're trying to integrate with that, how does that work to use that real-time data to get more instantaneous responses without doing the whole big MapReduce processing?
Yeah, that's a really good question. Actually, there's two schools of thought going on in this area. And one of them is that we'll make Hadoop faster. And the term microbatch has been thrown around as like, we're just going to make jobs, like the minimum runtime of a Hadoop job is typically like 30 seconds, something like that. And the term microbatch being saying, what if we can get it down to sub-second is one way of approaching the problem. But the other school of thought, and actually where most of the practice is that you don't use the batch MapReduce for those types of applications. And so there's some work from UC Berkeley on a in-memory platform called Spark, which is basically using in-memory, and you can do very rapid iterations on the data in intervals, and it doesn't need to go through MapReduce. So there you're using some of the file system technologies underneath, but you're not using the core MapReduce to do that. So that, Gemfire, a set of other in-memory technologies will bypass the MapReduce component to do the real-time. So that's I think the core of the real-time happens outside of that for the quick response, so we can turn around things in milliseconds. And by real-time, it's sort of that's the order of magnitude milliseconds. The other point of having the flow down from that is usually the output of those systems is to store everything, and there's some sort of ETL process into Hadoop. So even if you've got an in-memory grid that's storing and reacting to all this information, then you're pouring out all that information through ETL into something like Hadoop. And so if you're using HDFS and some MapReduce as a system to analyze that data, then you'll be importing that as fast as you can get it from those real-time systems. So that way the batch side of it doesn't impact the response time of the real-time system, but you still get to store everything, and you still get to do your post-analysis on the last 3 months of data. And then you can pump the results of that back out into the real-time system to react quickly.
Very good, thanks.
Yeah.
Other questions? So while you guys are thinking, you talked a lot about the machine-generated data and it taking over basically the volumes that we're likely to expect, and especially the velocity that we're likely to expect. What are we actually ready to handle that kind of volume? Do you think that the Hadoops and the mechanism that you talked about during your conversation today is ready for that, or do we have a lot more science and R&D and others to do before we can handle that kind of volume?
Yeah, it depends on what type. So you can just look at the pure scale of data. Hadoop's sort of been used in the orders of like low numbers of petabytes right now. But if you follow the growth path out, we're going to be at like the tens, hundreds petabytes. And there are very few instances that are that big, and I think there are particularly some bigger challenges that come there. Those we overcome. I think the bigger issue is like how do you build applications that can process the rate of events that you're seeing? So if you're trying to get like 1 million items a second coming in, how do you process that with context of all the other things coming into the system? So those require some particularly complicated in-memory grids to be able to do that. And if you look at where the academic research is, I think it's there and it's in machine learning. Those are the two areas that are still evolving. And I think we're not quite ready for the onslaught. We've got very customized things that are being built for things like Twitter, but in general, we're not ready for that level of mass. So a lot of interesting technology being built in those two fronts.
So from a closing remark, any other questions from the audience?
Yeah.
There's one right here. Go ahead.
Yeah, so do you know of any software that can do predictive processing? So you've got all this data, can you intelligently do some processing that you don't have to spend so much time?
Yeah, so the question is, are there any software out there that will do the predictive calculations on the data for you? There are a bunch, actually. A lot of them are coming from smaller companies that have grown up. There's one locally called Skytree, for example. There's a machine learning company. And they do things like sentiment analysis, so they'll automate the whole process of turning textual information into numerical scores and all the other processes that go through that. So there are a bunch of good companies that have the machine learning platforms to be able to process the data automatically. And so definitely worthwhile taking a look in that space.
Go ahead.
So given the fact that they have Walmarts and eBay and Amazons of the world have access to the same technology, where do you think the differentiating factors will lie eventually? Is it in the analytics part, or is it more in the technology side?
I would say that the differentiating technologies for economics and the first thing you want to be able to do is deploy new ideas, analytic ideas that give you competitive differentiation quickly. And so you need to be agile. And so the core ideas about what makes this company smart versus another are going to be high-level algorithms and thoughts about how to run the business and be sneaky against competitors and so forth. But once you've got that idea, you want to be able to take that from concept to production in as little time as possible. So people are going to have to be very data smart, and there's a lot. That's why the data science community is evolving so quickly. But having an agile platform underneath that is really key. So you want to be able to immediately collect all that data and be putting those things into production in months rather than having to wait a very long period of time. So it'll come from both areas. But I think the real core of the new ideas is coming in from the data analytics and data science community and all the algorithms that are being developed there, and then applying business problems to those at the top level.
Great answer. Any other questions? So as a wrap-up, if you can just talk a little bit about risks, what not to do, because not everybody should be worried about this level of scale. And for those that are in kind of like the middle area, any words of advice for what not to do, so you don't try to over-engineer, you don't make the 100 petabyte decision in most cases because it'll kill you if you're going to go in that area. So just some concluding remarks on risks and what not to do. If you just read the newspaper, it just seems like everybody should be worried about exabytes and this and that, but that's just obviously not the case.
Yeah, so I think the big thing is a couple of things. So you've got to really find a platform architecture that can scale quickly. And so you want to pick technologies which can start small and be sure that these are going to grow like crazy. And so you might pilot it this year. Don't plan for 20% growth next year. Expect that thing to be 10 times bigger next year. And so you've got to have a rapid platform, a platform that can scale out rapidly and support the amount of data growth and the applications you're going to put on top of that. The second thing is don't get locked into a vertical platform that sort of ties the application all the way down to the infrastructure. So you might get locked into a particular cloud platform or even a particular bit of hardware for that type of application. And if you do that, then it makes it really hard to say, okay, well, I've got this core analytics thing on the side or machine learning thing I want to run aside. Where do I run that? I don't have anywhere to do that. So we really want to be able to have a platform that is multidimensional, so we can have scale and we can have mixed workloads. And if you get that freedom in place, then you can pick and match the technologies that suit the developers, rather than sort of saying, no developer, you must use this platform. You can let them pick the best technologies for the job at hand.
Right. All right, that's terrific. Thanks
no
a
worries.
lot. I appreciate
Thanks a lot for the talk.
it was a great Q&A as well. Give him a hand.